thank you all for coming. Unfortunately, I can't see you because I see only black something in front of me, but I'll try to nevertheless speak about Kotlin coroutines. So, I'm Svetlana Isakova, I'm a developer advocate, and today I want to focus on Kotlin coroutines, introduce them, explain why it's so important feature in the Kotlin language, and show you some examples of how to use them. So let's start. The main purpose of Kotlin coroutines is to simplify asynchronous programming. And Kotlin coroutines, in essence, give us a new way to perform all these asynchronous computations. And it is not a Kotlin invention. The coroutine is not a Kotlin invention. The term coroutines, the concept of coroutines, is known for many years already, for many decades. And at the very beginning, it was used to emulate asynchronous computation, even on when we don't have multiple threads. And now Kotlin just reuses this concept, and we now have it in the language. And now I will explain what it is and why we have this. So let's start with the motivational example. And my motivation would be I'll start with the example for async await. And at first, let's start with this very simple piece of code. And it is very simple, consecutive, and straightforward, but it is wrong. The problem with this code is that loading image might be a very time-consuming operation. And while this image is blocked, if we perform this code, if we run this code from the main thread, our user might be blocked because it takes a long time to load actually this image. And there are different solutions to this problem. One of the solutions is to use callbacks. There are, you can use them directly, you can use different frameworks. However, it's still callbacks, and in this case, you have to extract what should be done when your operation is completed inside some lambda, and specify that this lambda should be invoked afterwards, after your code completes. And using these callbacks often lead to some not really nice, to different problems, especially concerning that the code is not easy to read, especially when you have a lot of callbacks one inside another, and sometimes it is called callback hell when you have a lot of indentations for these callbacks. And the solution to this problem, alternative solution to this problem, would be to use async await. And async await, in essence, allow us to avoid using callbacks here, and it allows us to just write this code directly. And if you look at it, it looks directly like our first wrong example. So it is very similar to it. So we just write the code consecutively, one instruction after another, without some kind of callbacks, and it somehow works. Note that I haven't yet explained you how this async await works. My first idea that I want to share is that we want to avoid callbacks, and the feature of coroutines and async await allow us to do that. Async await is also not a Kotlin invention. It is the feature already present in some languages, for instance, C#. And if you look at it in C#, this feature is a language feature. So these async await are language keywords. In Kotlin, they are not language keywords, but they are just library functions. And in Kotlin, it works on top of the concept of coroutines. So somehow the concept of coroutines allow us to have async await in the library and to enjoy the power of async await. Coroutines allow much more than just async await, and we'll discuss it a little bit later. But for a start, I want to focus our attention on this async await. So now I want to talk about what is a coroutine. So coroutines somehow allow us to have this async await. And I want to compare two concepts, the concept of a thread and a concept of a coroutine, and see what are the similarities with them and what are the differences. So in essence, a coroutine is very similar to a thread. So it is something that on the first glance looks like a thread. In which sense? Thread is a sequence of instructions, and multiple threads might be executed concurrently and can share some resources. And for coroutines, the same also works. Coroutine is also called a lightweight thread. That means that we can have much more coroutines, that we can create much more coroutines for our application than threads. So thread is a rather expensive thing. It requires a lot of memory, a lot of resources. And for coroutines, it's no longer the case. Coroutines are really lightweight, and we create like tens of thousands coroutines in comparison to threads in our application. So coroutine is something very lightweight. So now we know that coroutine is something similar to a thread, but we can have much more coroutines. Then let's discuss how they are different, how coroutine is different to a thread. And to explain this difference, I will use the following pictures. So in my talks, I will have lots of pictures today. I understand that it's second half of the day, so you might be tired. I hope that pictures will help. For my notation, I will use the following. So the thread will be the line always, and coroutine is this computation, and it will be drawn as this block. So the next level, the next understanding of how to think of what a coroutine is a computation that can be suspended. So it can be run on top of threads, in different threads, and we can suspend coroutines. So somehow we may take this coroutine from the thread, put it somewhere in memory, and later return it back. The question is, why do we need to suspend a computation? Why do we need to suspend a coroutine? And the answer is, even from this picture, you can see that when we suspend it, our thread is free. It can be busy with something else. So for another example, let's consider a situation when you start some two asynchronous computations from a main one, and you need to wait for the result. If you write this code straightforwardly via threads, like start from the main thread this computation, another one start them in parallel and wait for them, then while waiting for this computation to complete, your thread will do nothing, and your thread won't be able to do something else. And that's a problem. And if it's just a regular thread, it's just too expensive to lose threads in such a way. But if it's a main UI thread, it's even wrong because our thread is blocked and your user is also blocked. So that's why this situation with threads doesn't work really well, because you cannot write such code. It is readable and straightforward, but it's wrong because you're blocking threads. And coroutines allow us a very interesting thing. You can write very similar code to the one that you would write using threads. However, here you can suspend a computation. And in this case, when you suspend this computation, your thread is not blocked. And this thread can be busy with something else. If it's main thread, then it's like a requirement to have it available for all the requests from the users. So coroutine is a computation that can be suspended. And in Kotlin, we have the special marker to mark such computation that can be suspended. And that is suspend modifier. When you see a suspend function, that means that this function represents this computation that can be suspended. So now when you write code in Kotlin using coroutines, you will see a lot of such suspend functions. Now let's go back to my image example and the story of async await, and let's unwrap how exactly this async await works. First, we want to start a new computation while loading the image. So we write the function load image async, and this load image async starts somewhere loading the image, so it starts a new computation on some thread. We'll later discuss on which thread exactly it should start. And then when we use await, when we call await on this asynchronous computation, that will mean that this process image computation will be suspended and later returned and later restored. So await, if you see how await is defined, you'll find out that it is defined as a suspend function. So here we call async, and async returns us an instance of a deferred type. It's synonymous for future, something that is promised to complete in some time. And we can call await on such a deferred object, and this await is indeed defined as a suspend, which means that, yes, this is a marker that suspends our computation. So let's unwrap this example. We can extract this load image async into a separate variable to better understand what's going on. And here, at first, we started this loading image. We started new computation. And we have now two computations, one on the main thread that started another one, and a new one, like in my picture green one, that is loading the image. Then, when the code in the first computation reaches await, that is a marker that tells the compiler to suspend this computation if the result is not yet ready. So here, await refers to some computation of loading the image, and until the result is not ready, we suspend the main process image computation somewhere, and now our thread is free to perform another tasks. And then, when the result of loading image, when the image is loaded and the result is already available, then we can return, then the compiler returns automatically our suspended computation to a thread and continues it. So that's how async and await work. You may ask here, on which thread my suspended computation will be continued? And the answer to this is that you specify that. By default, the default thread pool is used, and that means that your computation might be continued on any thread from the default thread pool. However, you may specify that, okay, this is something that should be run only on the main UI thread, and in this case, when you suspend this computation, you continue it on the main thread. And note how our main thread might be busy with something else when our coroutine is suspended. So when we have this blue coroutine somewhere suspended, we can perform another tasks on the main thread. So that's our win. That's what we wanted to gain. Oh, sorry. So here, in this example, we probably set image on the main UI thread. So when we call async, we specify that this computation should be run on the main UI thread. However, there is another interesting story that Kotlin coroutines are not only async await. So here we see this pattern, and it is the feature that you might be already familiar with if you found it before in other languages like C#, and that's exactly the same functionality. This async await allow you to run something asynchronously on a different thread and then wait for its result. However, Kotlin coroutines are not only async await. you can do more things with Kotlin coroutines. And one of the most important things that you can do is you can define your own suspend functions. So now the way how you write your code differs from your habits can differ, because now you can think in terms of defining something as a suspend function. So whenever you have something that might wait and block a thread, instead you can now declare it as suspend function. An example. Here we have a simple consecutive logic. First, we want to log in our user to get some user ID, then we load some data using this user ID, and in the end we show the data. If we just write this code in this manner, in a consecutive, clear way, it will be wrong, because here we have two places where our user can be blocked, because we have here probably some network operations, and they may take a long of time, and during this time your user will need to wait. So that's something that we somehow would like to avoid, to block the user. So what are solutions to this problem? You can use completable features, for instance, to rewrite the same code and to allow to avoid this blocking user. Then you will need to use some API of these completable features, or if we are talking about probably Android or some other cases, you can also use RxJava. It also allows you to rewrite this simple, straightforward code in a RxJava style. However, for this simple case, when we just have some consecutive actions, like login, load data, and show this data, in this case, in this scenario, RxJava might be a kind of overcomplication. So if you compare the initial code with what we have with all these frameworks, you'll find out that with frameworks, it becomes less clear in some cases that are not probably intended to be processed in this way. So what we can do with async await? Now we have the power of async await, and we can rewrite our code, our initial example, using this async await functionality. And how we do it is now when we implement our login function, instead of just performing our login operation, we try to perform it like somewhere in the background, and return a deferred object that might be awaited. So that's how we program with async await. We say, okay, start this login operation, then await for it. And the same with load user data. So now we changed the return types of these functions, two functions, login and load user data, now return as deferred objects. And after each call, we simply await for the result. So our code, to my mind, it looks more clear than the previous one with the RxJava frameworks, but probably it's a matter of choice. So async await help us here to simplify this code. Okay, so also good. But with Kotlin suspend functions, we can do even more. In this scenario, we can simply define these functions as suspend function. And that will mean exactly that this suspend function, that is some computation that might be suspended. So whenever we access for user login, that is a network operation that might be long, and we want to be able to suspend it until it waits for the result. So we simply define our function as suspend function, and you see that the code afterwards, the code that shows user info, is the same as we had in the first wrong slide when we blocked the user. So that's what we have, that's the benefit that we have with coroutines. We had our first very simple code that probably you write at the first when you just need something to get working and when you are not very concerned with the performance. But then when you start to understand that, hey, user need to block, need to wait too much and is too slow, you may decide to convert it to the suspend function. You don't need to rewrite everything and to change the model. That is that is kind of slight modification. And you can, whenever you write it, you can define them suspend. At the beginning, when you understand it, yes, this is something that might be suspended, but the main idea is that it is very similar to it doesn't change the way how you write code. You just add these suspend modifiers, but everything else stays the same. So we just added these suspend modifiers, and IntelliJ also nicely highlights, and they nicely highlight the suspension points of this coroutine, of this function. So in this case, so show user info function is a computation that might be suspended, and it might be suspended in possibly in two places. And we clearly see where it can be suspended. At first, it can be suspended when we call login, because it is also suspend function, so that's something that can be suspended. And it can be suspended when we load user data, again, because it's some point which represents computation that can be suspended. So we clearly see these suspension points. On the declaration side, because we have the suspend modifier, and when we use them, because IntelliJ nicely highlights them. You may ask here, where can I call these suspend functions? And the answer would be that you can call suspend functions inside another suspend functions, like in the previous example. And inside, we saw already async. Async is one example of such Coroutine Builder. There are some others like launch. So these are called Coroutine Builders. And the difference, the main difference between async and launch is that async returns you like a deferred object that returns you some result. So for instance, here it is a result, we have deferred with that should return you an integer in the end, and launch returns you a deferred, some kind of deferred or future object without the result. So that's the main difference between them. So kind of launch returns you the deferred of unit, but there are different types. And if we look at how these suspend these coroutine builders are defined, we'll find out that they mark their lambda parameters as suspend modifier, also with suspend modifier. And then the right answer to the question where you can use your suspend functions is inside suspend functions or inside these suspend lambdas. But there's some kind of technical implementation details. You can nest coroutines inside, like you can start a coroutine inside another coroutine. So for instance, here we have the launch main coroutine, and we start async. We asynchronously load image inside this coroutine. And this moment, an interesting story begins, because there is like you may ask here, what about errors and what about exceptions? And what happens, for instance, if your nested coroutine, an error occurs in your nested coroutine, and will it be cancelled? Will the outer be cancelled, and so on? And the answer to this question, the solution to this, was finally introduced in a very recent update to Kotlin Coroutines. And like before, the general advice was that you have to handle it manually. However, now there is this concept of structural concurrency, and this thing also changes a little bit how you write your code using these concepts of Kotlin, of coroutines. So let's again look at some example. And here we have a classical example to show you two asynchronous computation. So we want to load two images, both asynchronously. So if you have enough threads, they will be loaded in parallel. And afterwards, when both of the images are loaded, we want to overlay them, to do something with both of these images. So we know now that we define this function. When we call first await, the main computation is suspended. Like for simplicity, I just I just say here that our computation is suspended once, but actually we have two await calls here, so our computation might be returned back, see that whether the second result is ready or not, and then suspend it again. So in this simple case, like that's fine, but what can possibly go wrong? And the problem here is, like, what happens if some exception is thrown inside coroutine? So while we are loading, for instance, the first image, the green one, what happens with the second image, for instance? And to answer that, first I need to tell you that, like, what generally happens with exceptions. Await just rethrows exceptions. So if your coroutine that you started throws some exception, you may catch it while calling await, and your exception will be correctly caught. If you don't so you can simply use a regular try-catch and surround this await function with try-catch to process this exception in the correct way. If you don't catch this exception, then it will be simply rethrown further upper. Like await just rethrows this exception. The problem is that if, for instance, an exception is thrown when your first image is loaded, then no one says the second image to stop loading. So no one canceled the second started process if you don't do it somehow manually. By default, nothing happens. So this exception is thrown upwards, and probably you want, in this case, to stop everything, to cancel all the started tasks. But by default, and like before this introduction of structural concurrency, this was indeed a problem. But now, with structural concurrency, we can say that, and actually not only we can say, but by default, all our coroutines that we started as structures are structured, and you start a coroutine in some outer scope. And in this case, like you see, there is the difference from the previous example is that we introduced, we are using now this coroutine scope, and the difference is that now, if one of your children coroutines is cancelled, then the outer scope, before returning, will clear up everything, will wait until its children are finished, or will cancelled if it's cancelled. So now these children coroutines are cancelled automatically if someone cancels their upper coroutine. And even in this case, when an exception is thrown in one of the child coroutines, it also means that the parent coroutine is cancelled unless it processes this exception correctly. So now with structured concurrency and with introducing of coroutine scope, you can specifically specifically start your new coroutines in some context, and they are and they are automatically processed. Their life cycle is depending on their outer scope. The difference that was introduced in this late release, so probably if you already used Coroutines, you know that you can use async await directly from any point. And that means that these new coroutines are started in some global scope. However, now after the latest difference in and in Coroutines 1.0, there'll be these async and launch functions are defined as extensions on this scope. And whenever you launch or whenever you start a new coroutine, it's always started in this scope. So by default, you may specify, if you don't have some scope, you may specify that, okay, start my new coroutine in the global scope. So that might be a default option, but a little bit later I'll show you the better solution. So the difference is that now your coroutines are always binded, are always connected with the scope. And now, whenever you want to start a new coroutine in somewhere, in some other thread, some new asynchronous computation, you have to explicitly say that you have to explicitly define this function that starts a new coroutine as an extension on coroutine scope. So that's another difference that that brings this structured concurrency approach that influence how you write your code. So now, when we write this function load image async, and it starts a new coroutine, this loading image will be connected, will be binded to this outer scope, depending on what scope we're starting it from. In this case, we just used coroutine scope function, but the supposed way how to, like, where to bind all your newly started coroutines, all your newly created computations, is there is this question where to bind them, and the answer is that often you have in your application some objects with a well-defined life cycle. So if we are talking about Android, such object is an activity. So an activity is an object with a well-defined life cycle. When we're talking about some other frameworks, there are always there usually some this kind of something with life cycle, and we can bind all our children coroutines to this life cycle. To accomplish it, you do a very easy thing. So, for instance, you can implement by your activity coroutine scope. And if you implement coroutine scope, then you can start all your new computations. Do remember that now we can only call async and launch from some coroutine scope, because they are extensions to coroutine's scope. And now, because our activity extends coroutine scope, we can simply call async await, async or launch, or call our custom functions starting new coroutines from this activity without any specification. So after you correctly define this scope for your class, then you can easily call this async await from the class, easily create new coroutines from your class, and they will be automatically binded to the life cycle of your class, of your object. So that's the core difference. Now, with structured concurrency, the life cycle of your coroutines is correctly covered, and it is bound to activity, to activity or another object in your system with its own life cycle. So I've shown you just implement the coroutine scope, and now how to implement this coroutine scope. That's also easy. That's just some pattern that you may use for your application. So whenever whether it's activity or some other class, the task is very easy. So you implement coroutine scope, and then you want to do some little ceremony when you create your instance of your class with lifecycle and when you destroy it. So in the case of activity, we have on create and on destroy. And on create, we create so-called job. So job represents the lifetime of the activity. And in this case, we created we create this job, and whenever inside your activity you call either async launch or your custom async functions, they are bound to this job. They will be automatically bound to this coroutine context because you here overloaded this coroutine context library. And when your activity is destroyed by calling this job cancel, you simply cancel all the children coroutines. So that's the main idea, how to control your children coroutines from your application. There might be a question. What is the difference between, not what is it, but when to use, when to define something as a suspend function, or when to define something as an extension to this coroutine scope? Because I've shown you that now it brings you the new way to structure your code and to write your code, because now in your application you define some functions as suspend function, meaning that they might be suspended because they require some job for something. If you usually your such functions may use some API that might be blocked, that requires callbacks, but there is a way how to use such API, rewriting it to such suspend functions. So you basically add some additional methods to the function, to the library, some library functions that are written with callbacks, and afterwards you use them from this coroutine model. So, but then let's go back to our question. Here we have a suspend function. We can now write some functions as suspend functions, and we also can start some new coroutines. And we know that when we start some new coroutines, we define it as a coroutine scope function. And they're proposed a way to distinguish between them and to decide whenever to use which is that when you define your suspend function and you are interested in its result. You are interested in its result immediately. Then you define it as a suspend function. So here you probably remember in my first example with this login, when I defined it as something that returns deferred, I have to call await right away. And this is a kind of marker that, yes, in this situation, suspend works better. But when you start some new computations, when you start new asynchronous computation, one asynchronous computation, or probably it will be several asynchronous computation, and then you either not interested in the result whatsoever, so they will just continue to compute on their own, that's fine, or you are interested in its result sometime later. In these cases, you are defining such function and as an extension on a coroutine scope. And the rule is like the convention, so it's like kind of a convention. The convention is not to mix the two, so not to define extensions on coroutine's scope as suspend functions in order to clearly understand the purposes of the functions concerning this suspension coroutines model. So that's new suggested ways of writing your code that might be suspended and that may require this suspension mechanism. Some implementation details of how these coroutines are implemented under the hood. So whenever you write some suspend function, under the hood, this suspend function in the bytecode level takes additional parameter. So it is generated to take this additional parameter, and the compiler automatically generates this parameter. So if we look at continuation, it's kind of a generic callback interface. And to some extent, coroutines work through the same callbacks mechanism like before. Like when we started discussing that you can solve such problems with callbacks. However, now all these callbacks are hidden by the compiler, are hidden in the bytecode implementation of this function, and the compiler generates all these callbacks automatically for you. So that's one way to, like one simplified way to think about it. And when we're looking at like what is this continuation? So I show you that here we have some hidden parameter continuation, and what is this continuation? When we suspend a function, so for instance in this example, I have a function, and the first line login is my first suspension point. So when I suspend a function here, when I say that computation is stored somewhere, like this continuation interface, continuation object is stored, and it contains all the information of the exact point when we stopped this computation, when we suspended this computation. So this continuation contains information of the values of the local variables, of the parameters, the point where in the function are we, so that's automatically stored. So in a way, the rest of my function after the suspension point goes inside this generic callback continuation. And when we restore this function, it continues from, it restores its state and continues from the point where it was suspended with the newly results that we got from this suspension function. So the same works for the second suspend point. Here we have another, like the rest of the code becomes continuation, and for the same for the last suspension point, again, the rest of the code becomes this continuation. Another implementation detail is that the body of the coroutine is compiled under the hood to a state machine, and basically the number of suspension points that you find inside a function. So that's here we don't know how many suspension points do we have, because we don't know the implementation of login function, of load user data, etc. But when we store this this computation, this coroutine, it is implemented via the state machine, and each suspension point is one of the state. So when we reach first suspension point, we suspend the coroutine and then restored it, etc., etc. They continued to perform the code, reach the second suspension point, suspended it, restored it later, etc. So that was almost all about what I wanted to share about coroutines. some like Kotlin coroutines are much even more than just async await, then suspend functions and the exact coroutines. So again, the concept of coroutines lives in the language. So this language supports the suspend modifier for suspend functions, Coroutine builders like suspend lambdas, and some ways to, and all this magic of suspending the computation and restoring it back. And everything else is built on top of it and lives in the library. So there is async await. There are also the support for more complicated concepts like channels or actors. You can also implement that via coroutine and use them. And there is a separate thing as yield. Yield is also in Kotlin implemented via coroutines. You can find information about coroutines in our site. So now you can read everything about them there. And also, I would recommend, if you want to learn more, there are talks at KotlinConf by Manuel Zarev, who is the lead developer of the Kotlin libraries, including Kotlin Coroutines. And here he explains this concept. And in the last talk at KotlinConf, he explains this concept of structural concurrency in detail. So if you want more about it, you can try it. So thank you very much for your attention, and have a nice Kotlin with coroutines.